I guess most or all of you are new to Stanford, is that correct? Who's been here? So most of you are new. Okay, well, welcome to the new ones and welcome back to the ones who've been around. This sounds like a great week that you're enjoying, a really nice broad-based exposure to a lot of what's going on here at Stanford. And what I'll talk about in the next 15 or 20 minutes and then have some questions on the topic is kind of an overview of carbon capture and storage. And I'll use this both to describe the process of carbon capture and storage, just kind of what it is in a few slides, and then also to kind of use it as a launching point to talk a little bit about subsurface flow, because the whole storage problem with the carbon capture and storage involves subsurface flow, which also ties into enhanced oil recovery of any sort, really, water resources, etc. So it's, I'll try to touch on a few of those things. Okay, so the idea in carbon capture and storage, this is kind of an overall schematic, and I'll go into a bit more detail on some of the particular procedures here. But let's imagine we have a coal-fired power plant. So the way you actually generate electricity from a coal-fired power plant is to burn the coal, creates a lot of heat. You boil water, creates steam. The effluent then would be, since the coal is burnt in air, the effluent flue gas would involve the CO2 from carbon plus oxygen yields CO2 plus the nitrogen in the air. Air is 78% nitrogen. So the idea then, rather than just vent all that flue gas to the atmosphere, is to actually capture the CO2. So that's this capture step here. Then what gets vented to the atmosphere is more or less something approaching a fairly pure nitrogen stream. Then the CO2 gets compressed and pipelined somewhere where it can be injected into a subsurface formation and stored ideally over geologic timeframes. The idea is to put the CO2 in the subsurface and never see it again, have extremely low leakage rates, like 1% over 1,000 years or less, things of that order. So that's kind of the big picture. So if we look at it sort of schematically, this is more or less what I just said. We've got air plus fuel. We can think of it as coal, but it could also be natural gas. We're burning a carbon-based fossil fuel here. There's the boiler. We generate steam. It turns a turbine and provides electricity. This would be a parasitic CO2 capture, the idea being we would pull off some of this steam and use that as the heat source, which I'll talk about in a minute, for actually performing the separation between what comes in as CO2 plus nitrogen plus perhaps some water, and what leaves here is the nitrogen and water, and what leaves here is the CO2. So the idea is to get a relatively pure stream of CO2, which can then be injected into the subsurface. So there are various, so yeah, I should make the point here that obviously there's an energy penalty, right? Because some of the steam that could be used to spin the turbine and generate electricity is now being used instead to capture the CO2. So here's just kind of a quick schematic of the process for capturing the CO2. The idea is, you know, here comes the flue gas. Think of it as basically CO2 plus nitrogen. At relatively low temperatures, this is what's called a temperature swing absorption process. At relatively low temperatures, the CO2 contacts a lean amine solution. At low temperatures, the amine picks up the CO2, so it absorbs the CO2. Then in the stripper column, the temperature is higher, and when the temperature increases, the amine releases the CO2. So the idea is the nitrogen just basically bubbles through off to the atmosphere. At lower temperature, the CO2 is captured. Then at higher temperature, now you can see where the heat is required, the CO2 is released, it's pressurized, it's sent off to the pipeline, and we can inject it into the subsurface. So you see where the energy penalty is coming from in order to capture this CO2. Another approach, which I won't talk about at all, but it's a common question, is, well, why not separate the air to begin with, rather than, since we've just got this nitrogen going along for the ride and then we have to separate the CO2 from the nitrogen, why not just burn the, say, carbon in the coal and oxygen. That's another approach. It's called oxy-fuel combustion. Then you've got the energy penalty of having to separate air into oxygen and nitrogen. So that's also something that's being actively investigated, but of course there's an energy penalty associated with that air separation as opposed to the separation from CO2 and nitrogen. Okay, so now the CO2's been captured, it's been pipelined. What do we do with it? Several possibilities, and this kind of is a cartoon showing a few of them. One idea, and this will probably be used in some of the early CO2 storage operations, is to put it into depleted oil and gas reservoirs. That's shown over here. This is, you know, a well, and that's supposed to be a trap. The attractive aspect of doing it that way is that a depleted oil and gas reservoir has demonstrated that it can store fluids over geologic time. So we expect that leakage probably won't be a problem there because oil and gas were stored in that formation over thousands, millions of years. Another one, also very attractive, is to use the CO2 for enhanced oil recovery. EOR, or enhanced oil recovery, entails injection of something other than water into the in situ oil in order to facilitate production. CO2 works very well for that. So some of the CO2 that's captured could then be used for EOR. And the third one, and this is the one where there's really big targets around the United States, is deep unused saline water saturated rock. So the idea is, if you know, in many places in the US, if you drill down far enough, there are what are called brine aquifers. So an aquifer is a rock formation with salt water essentially in the pore spaces between the grains. That makes a very big target for injecting CO2. There's a lot of available pore space, and that's where presumably a lot of this captured CO2 will get injected if this ever does indeed occur at scale. So let's talk a little bit about how flow in the subsurface works, and then we'll get back to the CO2 storage problem. So the way to think of these formations, a lot of people kind of have this image that you drill down, say if you're producing oil and there's this pool of oil. That's not how it actually exists. The oil or any fluids in these formations essentially lives in the pore spaces between sand grains. So think of a bucket of sand, and imagine if you pour water into that bucket of sand. Where does the water go? The water goes into the space between the sand grains, and maybe something like 30% of the volume in a bucket of sand is actually open to the water infiltrating it in that particular scenario. So something like 20–30% of the volume is pore space into which fluids can be put. So if it's a saline aquifer, then maybe 30% of the volume, 25–30% of the volume is this saline that then we can inject the CO2 into. Okay, so flow in the subsurface is governed by what's called Darcy's law. So Darcy's law basically says that velocity, there aren't going to be too many equations, but there are on this one and the next one, and then I think I'm done with equations, so just stick with me here. So Darcy's law says that the velocity of fluid is proportional to the permeability, which is a property of the rock. It's like a flow conductivity, divided by viscosity times a pressure gradient. The other important concept here is porosity, which is the volume of the pore space divided by the bulk volume, like the example I just gave of the bucket of sand. So what we do when we simulate flow in the subsurface is we basically write Darcy-type expressions, Darcy velocity expressions, for the different phases that are flowing. If we're injecting CO2 into saline, saline is just salt water, so we'll have an equation that describes how the gas moves, an equation that describes how the water moves subject to a pressure gradient, and then we'll combine those with statements of mass conservation. So this is just a partial differential equation for a particular component, gas or water, this is an accumulation term, a flow term, and a source term. Those balance, that's a statement of mass conservation. We combine that with our Darcy's equation. We would have two partial differential equations that we then solve in space and in time to tell us how these fluids move through the subsurface. Very similar equations if we're trying to simulate how oil moves through the subsurface. Very similar equations if we're injecting CO2 into a saline aquifer. So in order to do these models, we need to first construct essentially what's sometimes referred to as a geological model or a geological realization. We, of course, don't really know all the details of the subsurface geology. There's relatively sparse measurements. It's a whole science and art as to how these geological models are actually constructed. Each grid block in the model has to have a permeability and a porosity and some other properties. But then once these geological models are constructed, we solve those equations I just showed. And this would be, for example, it's maybe hard to see, but there are a lot of wells in this model. And by essentially setting pressures in the wells, we can produce oil, we can inject water, all sorts of things. So these kinds of subsurface flow models, which again entail a geological description coupled with a discrete representation of those flow equations, enable us to model and optimize oil and gas production, to design enhanced oil recovery processes that could involve injection of CO2 to both store the CO2 and to produce oil and gas, and also enable us to perform modeling and optimization of geological carbon storage operations. So let's look a little bit now, focusing in on the carbon storage aspect of this. This is a plot of, so here we have this in situ salt water basically, and we're going to inject CO2 into it with the idea of, or with the expectation of not seeing the CO2 again in the atmosphere. So the way the CO2 is stored, which is sometimes referred to as trapping in this context, is by a variety of mechanisms. The CO2 is less dense than the water, so what can happen is the CO2 just rises up to the surface and ponds against, just rises up to the top, what's called a structural trap. So the CO2 would just rise and then get essentially stuck at the point where there's impermeable rock. That's called structural trapping. There are also other mechanisms. Solubility trapping means the CO2 dissolves, so we basically get bubbly water. So that's solubility trapping. There's something called residual trapping, where the CO2 plume gets separated enough that it can't flow. So that's also a relatively safe mode of trapping. And depending on the rock and the chemistry, over much longer time periods, we get what's called mineral trapping, where the CO2 eventually reacts with the rock. Now, so this is time since injection stops. It's a log scale, so it goes from 1 year to 10,000. You see mineral trapping is really picking up over the 100 to 1,000 to 10,000 year time frame, so that's way out. These other ones are occurring over shorter time frames, but at the early part, a lot of it has to do with structural trapping. So a lot of the CO2 is just moving to the top of the formation, and it's held in place by an impermeable rock region. Now, the idea then is to, our expectation is that there's no fracturing, no holes poked in this trap, otherwise the CO2 could leak. Ideally, we would like to facilitate these other modes of trapping, either residual trapping or solubility trapping, if possible, because that would lead to a safer storage operation. So the idea is to move further out on this plot relatively quickly, if possible, in order to minimize the risk of leakage associated with the CO2 storage. So let's see how we can actually approach that. So this is work that my recent PhD student David Cameron did, who just finished his PhD a few weeks ago. So he worked on optimizing CO2 storage operations, and the idea was to determine where to put wells and what sort of injection schedule to use in order to minimize the amount of mobile CO2, and that's the CO2 that's most susceptible to leakage. So we're trying to store more of the CO2 using these mechanisms and less of the CO2 using these mechanisms. And the kinds of results he got, of course I'm not going to go into a lot of detail on the formulation, look something like this. So we're determining where the wells should go optimally, and also how the wells should inject CO2. So we had 4 different wells, and this is showing the injection rates over 4 different periods. So the thing you'll notice is, for example, well 2 doesn't inject in the first 2 periods, then it injects a lot. Well 3 injects a lot in the first 2, then it doesn't inject. So we're not injecting uniformly at all, and by varying the injection rates, we're able to get a safer storage. And what this shows here is the mobile CO2 looking down on the formation. So red is bad here. We would like to not have red because more red means more mobile CO2. What you see using just a kind of default setup where we just place the wells in what seem like reasonable locations and inject uniformly, we get a lot of red, a lot of mobile CO2. Using the optimized setup, there's clearly some improvement. There's less mobile CO2 by doing this computational optimization. This is an example of how we can reduce the mobile CO2 even further. So this is the CO2 injection process. We're going to inject for 30 years, then let the CO2 equilibrate for another 1,000 years. So here comes the CO2, shown in red as mobile CO2. Notice at the beginning, this well 2 here isn't injecting, if we saw that from the previous. Now here it is at 15 years, at 30 years, okay, now we're finished injecting. At 60 years, it just continues to equilibrate. Now what we do is after 300 years, we basically stir up this big formation. So we produce brine at the bottom of the formation and inject it at the top in order to expose some of this mobile CO2 to this re-injected brine. It's like a very large-scale stirring. And we do this in an optimal way. We optimize this process. So let's see what happens. Remember, mobile CO2 is bad. We'd like to eliminate that. Now we're injecting brine, doing this stirring. Well, now there's less still. After 600 years, it does come back somewhat. But notice that the amount in 600 years is quite a bit less than the amount at 300 years. So that's the idea of engineering and then optimizing these storage operations. We have a particular goal, which is to make it less risky. We use flow simulations and computational optimization in order to facilitate safe storage modes. I'll just very quickly talk about detecting leaks, and then we'll quit and move to questions. So, of course, there is always some risk of leakage, and if leakage does occur, we would like to detect it quickly, and in order to be able to remediate or change or something. So the idea here is, how do we actually detect leakage? So we're looking at scenarios where we've got monitoring wells in the overlying formation where we can measure the pressure with the goal of seeing if we can detect leakage when it occurs, by solving an inverse problem. I won't get into the specifics, but this is an example of the true model. So this is the leaked CO2 into the formation above the storage formation, and this is what we come up with using this pressure data. So not perfect, but we are able to determine that a leak exists by monitoring the pressure in the overlying formation. And we've looked at some examples with larger numbers of leaks. Basically, we can pretty much find the largest leak. Some of the smaller leaks we don't get quite right. Sometimes we do, sometimes we don't, but we can detect relatively large leaks. Okay, so let me just summarize, and then I'll just give a quick idea of some of the classes you might want to explore within ERE. Carbon capture and geological storage represents, if done at very large scales, represents a means for limiting CO2 emissions to the atmosphere. The carbon capture and storage operation entails an energy-intensive separation. This is going to cost money, capital cost plus operating cost. Then injection into the subsurface, and then long-term monitoring and remediation if necessary. So interestingly, the cost really comes in the separation. The risk comes in the injection into the subsurface. So it's an interesting problem in that regard. And subsurface flow simulation and optimization, as are used in a variety of application areas, specialized to the carbon storage problem, could be essential for designing and managing these processes. Okay, just real quick, some of the relevant ERE courses, and these are not just courses that I teach. There's actually a class taught by Sally Benson and Jen Wilcox on carbon capture and sequestration, fall quarter, Energy 253. So if this sounds interesting, check it out. Then I teach a class on, and several of these are co-taught, reservoir simulation and advanced reservoir simulation. So that's actually how do you do these computations. Another relevant class perhaps might be that Energy 101, Energy and the Environment. It's undergraduate level, but probably a good survey overview class. I think I heard a ding, and I think my time is up. So I will quit there and be happy to take any questions.
carbon capture and storage could be good if it was done on a grand scale. Can you elaborate how grand?
If I'm recalling correctly, to do something like a wedge, are you familiar with the wedge concept? Okay, to essentially get up to about a gigaton of CO2 captured, which would be like order 10% of the problem, we would have to capture volumes of CO2, capture and store volumes of, so this would have an impact. It wouldn't be the total solution, but it would be a chunk of the solution. We would have to capture and store volumes of CO2 approaching the volumes of oil that we use on a daily basis. So it's big. It really has to be done at serious scale to have a big impact. But on the other hand, when you look at, say, the number of the increase in the size of the energy system that's anticipated to occur over the next, say, 30 to 50 years, those are huge numbers as well. So, I mean, they're all scary numbers. And for this to have any effect, for anything to have any effect, the scales have to be enormous. Yeah?
At that scale you just referenced, what is the corresponding increase in price over burning coal without cooking?
Yeah, so this is not something that's my area, so it's economic people and policy people and you know, engineers as well discuss a lot what the cost of doing this is going to be. The kinds of and of course it depends if we're talking in early stages or once the technology is mature. I mean, sort of a rough number might be like a 50% increase in electricity, in say coal-fired electricity cost. So not insane. And usually the follow-up question I ask people is, what was your electricity bill last month? And no one ever knows. So if they were that concerned about their electricity price, everyone knows the price of their house, the price of their car, how much they paid for gas. But you know, I think we could sustain somewhat of an increase in electricity price without, you know, economic devastation. But it would be noticeable. Yeah.
Could you speak to some of the current CCS pilots and how they've
Yeah, so the big one is the Sleipner project, which is in the North Sea, started in, I believe, 1996. It's been operating for quite a while. That one was a great sort of starter project. It's when you produce natural gas, sometimes there's associated CO2, and there's a limit as to how much CO2 you can essentially put in the pipeline and then you know, sell it as natural gas. So I don't remember the exact numbers, but in this Sleipner project, they're producing natural gas that's high in CO2, so they have to do CO2. They have to separate out the CO2, and then rather than vent it, there's a carbon tax. This is Norway, offshore Norway in the North Sea. They inject it into another formation. So that's been, I think, viewed as very successful. It's been monitored with what's called 4D seismic technology. It's kind of like doing an ultrasound of the Earth repeatedly, so they can actually monitor more or less where the CO2 plume is going. And then there's a lot of data, so they can actually model it. If there is some leakage there, it's you know, it's a little bit less of an issue because you're however tens of miles offshore. So you know, the impact is going to be not direct, certainly on humans. There's another big project in I think Algeria, in Salah, again associated with natural gas production. I don't know quite as much. That one's run, I think, by BP, so the data isn't. I'm just not quite as familiar with that one. And then there are a lot that have been suggested. Unfortunately, they're not really coming online quite as rapidly as a lot of people would like. The technology seems workable. It costs, and you know, you always have it's not the not in my backyard, not under my backyard, but you have those sorts of concerns. Yeah.
So you mentioned re-injecting brine down into the well at something like 300 years. How important is that step, and how realistic is it to expect that would actually occur?
Well, so Yeah, good question. I mean, it's the way I sometimes view this. I skipped this one, but now you've given me a good excuse to come back to it. This is essentially what's sometimes called a Pareto front in a bi-objective optimization problem. So essentially you can think of it as the optimal trade-off between risk and cost. So risk is the mobile CO2 fraction you're comfortable living with, and cost is how much of this brine you want to cycle, measured in pore volumes. Once we're out here, these are staggering volumes. These are enormous volumes. But what this says is, let's say somehow I determine that, so with no brine cycling, I get this to 0.22, for example, just injecting it optimally, as I described. If we do brine cycling, then I'm out on the curve. So let's say you decide, well, I really want 0.1 mobile CO2, that's the most I can live with. What this says is that the minimum amount of brine you would need to inject is, whatever this is, like 0.07 pore volumes or whatever that comes down to. So it gives you the trade-off between cost in order to reduce your risk. And this is what a decision maker is going to have to decide. I mean, or we as a society are going to have to decide. And there's, for whatever approaches you apply, there's going to be trade-offs, right? Obviously, it's going to cost. So this sort of approach is how one could begin to think about that sort of thing. If you say, well, no, it's all too expensive to do this brine cycling, then you'd be up here. And if you're willing to sort of cycle enormous, staggering volumes, you could drive it way down. Yeah.
But how are you to expect someone 300 years down the line to still be working for that company? Or
so this is a good question. And not me, but people have thought about how the risk on this should work. Sort of who's responsible, whose problem is it? Some of the things that are proposed is that some company will operate this for some, say, tens of years during the injection and maybe early equilibration period. There you're talking, decades to half a century. And then maybe it will be, run by the government, for example. And there would be long-term plans and long-term monitoring. I mean, there'd be monitoring that would be done that would maybe tell you if these things, if you needed to take some of these steps or not. Like that's this idea of this 4D seismic. That's the idea of having those monitoring wells. Oil fields, oil fields exist. There are fields in operation in California, correct me, Roland, I think for over 100 years, from the early part of the 1900s. So, this is done on the decade to century time scale. Yeah.
How dependent is CCS on CO2 transport infrastructure?
So the transport infrastructure will need a lot of pipelines. Yeah, I mean that's for sure. Now you could think about sort of co-optimizing. Let's just say we're going to burn coal. I don't think we're going to be building a lot of new coal plants in the U.S. in the near future, but just imagine we were. Then you could sort of optimize where you build the plant relative to where the injection target is. And you could, people have thought about how to optimize this pipelining problem as well, given where the coal is and where the power plants are going to be. So a lot of things are linked, Stuart, you like this, where the grid is, where the coal is, where the pipeline is, where the target is. All those things kind of will combine in addressing this. Okay? All right. Thank you.